Good afternoon, everyone. Charlie Kim from Korea Institute of Science and Technology. I'd like to thank the organizers for giving me this opportunity to be here. And in this presentation, I'll be talking about the work that has been done in nano-MRI at KIST, and hopefully its possible application to study electron transport in two-dimensional systems. This work was done in close collaboration with Professor Dong-won Lee at Korea University and Dr. John Layman and Dr. Dan Ruga at IBM Research Center. I will start with what we are working on in nanoscale MRI. I will not go too much into the technical details, but I hope to give you a clear picture of what we are trying to do and what this approach can offer. And then I'll move on to how this is connected to our wide field view experiments with ensemble emitters. And in the end, I would like to share a few thoughts on how this line of research could be applied to study electron transport in two-dimensional systems. Actually, lately, I have been having lunch with Professor Son. So actually, he came up with an idea out of those lunches, and actually, although it's a bit rough idea, but I thought this symposium would be a good place to share it and hopefully get some feedback from the real experts from here. So this is the dream of nano-MRI. These are the motivations we have in this work. So the idea is taking this technique, which can look below the surface in 3 dimensions non-destructively, and shrinking it from millimeter scale to ultimately be able to look a molecular complex like proteins. So it's a very challenging order. You need a really good transducer to do that. Just to set the scale, a field from a single proton at a distance of 10 nanometer is 3 nanotesla. So you need a nanotesla sensitivity to look at it, and it's gotta be very spatially localized. While traditional MRI relies on signals from thermal polarization, nano-MRI typically measures statistical polarization. Thermal polarization arises from the alignment of nuclear spins in thermal equilibrium along a magnetic field. However, whereas the statistical polarization results from the randomly oriented magnetic moments, but it's statistically polarized at a specific time. And so to better understand the relative significance of these two types of polarization, we calculated the magnetization from the thermal and statistical polarization as a function of the number of nuclear spins. As you see, when the number of nuclear spins is large, the magnetization following the Boltzmann distribution dominates. But with the small number of nuclear spins, you can see the statistical polarization become more significant. So that specific regime is exactly what we are interested in. So we are using nitrogen vacuum center in diamond for nano-MRI, the so-called nano-MRI. So these background image show you typical luminescence image we have. So we can use this to locate each ND center. The ND center is a point defect consisting of a substitution nitrogen atom with a vacancy in its neighbor lattice site. The laser that gives you luminescence also initializes the spin state into MSA equal to 0 state. And also, thanks to its spin-dependent fluorescence, we can figure out, by counting the number of photons, we can figure out which spin state it is. And also, it also exhibits remarkably long coherence times compared to other quantum platforms, even at room temperature. Simply speaking, we shine the green light in and detect the red photons out, and by counting the number of red photons, we can determine its spin state. And the spin state is manipulated via electron spin resonance through the application of the external microwaves. And finally, we can detect the target nuclear spin via nuclear magnetic resonance. So this is a schematic of our customized confocal setup. So we use 532 nanometer laser is modulated by this optical acoustic modulator, and also the scanning is carried out by this fast steering mirror. And the system is configured to ensure that only the red photons, which has longer wavelengths than 630 nanometer, are collected by this APD. So these are the photos of our lab. Although it's not perfectly organized, you can see this black box houses the customized confocal system we have. And you can see a lot of instruments. And the whole thing is temperature regulated. So by the PID, and it's stabilized to within plus minus 0.01 degrees Celsius. So this is what the apparatus looks like inside the box. We have a diamond over there. We use a diamond, CVD grown diamond, which has a 2 millimeter by 2 millimeter size. The thickness is 150 micrometer. And right above it, we put an antenna to apply the microwaves. And we use the microwave guide to efficiently deliver the microwave. And then we have a magnet here, and we have a scanner made from the additive. And we have we built this 24-based target approaching system, which I'll explain later. And also we put a PID control system inside the box. So as a first experiment, we wanted to simply detect the nuclear spins. So before you can image, you have to be able to detect. So the idea is to take a blanket film of a polymer, like PMMA, that contains lots of protons, and put it on top of diamond, which has shallow NVs. In this case, we use about 5 nanometer deep below the surface. Then we detect the Larmor frequency of the target. And we do it with this multiple sequence, which has a lot of pi pulses that are spaced synchronously with the Larmor precision frequency of the target. This measurement is actually based on measuring the statistical polarization of the nuclear spins near the NV center. The next
sample measurement or single
spin.
It's a single spin. Yes. So you just focus on the one of the sample.
Yes. Okay. So the net magnetization of a small set of nuclear spins is zero, but has a sizable standard deviation. And those excess protons become statistically polarized and undergo Larmor precession, generating an oscillating field, which we are trying to detect. So then the superposition state of the NV center evolves to a non-zero random phases under this fluctuating magnetic field. So we design the measurement in such a way that the variance of those random phases is made sensitive to a specific frequency. And in the end, the superposition state with a certain phase accumulation is projected to one of the eigenstates, which gives us fluorescence. This so-called quantum locking detection enhances sensitivity to an oscillating field at a certain target frequency, then suppresses other fluctuations at every other frequency. So in the below, you can see a representative data. So you can see a pronounced dip at the proper tau. And by fitting the data with our theory model, we can extract key parameters like root mean square value of the B field or the depth of the NV center. So if you change the B field, the deep shifted as it should, the slope is 42 megahertz per Tesla, which is the correct gyromagnetic ratio of the protons. So we know there are protons near the NV center.
Sorry, I got a bit confused. I think this statistical polarization does not depend on the magnetic field.
Yes, they do.
They do. As a square root of p?
Yes.
I see. So that's okay. Yeah. So they still do changes.
Yes.
But it's a square root of p, not the linear p. So
Actually, this frequency is the Lamarck frequency of the photons.
I see. Okay. So that's it.
In terms of where the signals are coming from, you can calculate the point spread function. So as you see, most of the signals originate from a depth of approximately 2 nanometer. So it's only sensing a very shallow region, and that's because the field folds up so quickly. Since we are detecting unpolarized nuclear spins, we have to sense b squared, which goes as 1 over d to the 6th. Similarly, the lateral resolution is of the order of the depth of the epicenter. So to get help both of these, we would like to go even shallower. So we have to take the next step. So we took a PMA particle, which is the target sample, which can be scanned over the epicenter. So we still use a Strabon D. This is also about 5 nanometer gauge millicentrics. Yeah. Then we also built a scanning system, target recruiting system, called before. So we built a target recruiting system using this tuning fork, which is driven by an self-oscillating circuit. So by monitoring the shift of the resonance frequency of the tuning fork, we can determine when the target makes contact with the diamond surface. Also, to calibrate the scanning system, we use an electron pattern sample with known dimensional information. Then now we want to do imaging. So for imaging, in the measurement sequence for imaging, we use the correct tau to match the Lamarck frequency to target nuclear spin. In this case, which is 1.6 megahertz. Then we do this protocol as a function of position. So here's as a function of tau, which is pronounced it at the proper tau. So it's tempting to take that point as a signal, but you have to be a little bit careful because this curve can shift up and down for a variety of reasons. So what we did was take 3-point measurements, on and off measurements, and take that relative as a signal. So if you look at on the left, you can see a close-up of the target analyte, which is PMA particle. If you look at the end of the probe, you can see a tiny shaft of a PMA that tapers down to a point, which is well below 1 micron. So that's our scanning object. So we scan it by bringing it down and doing our measurement protocol and bring it back up and moving laterally and to repeat the process. So this approach effectively minimizes the wear and the deposition of the target material. On the right, you can see the result of one directional scan. So the edge of the PMA particle was scanned at every 8 nanometer. And the spatial resolution of the system is primarily limited by the scanning system itself rather than the sensing mechanism. So we are still searching for suitable target to test our system's performance. One potential target is the bacteriophage, you can see on the left, because the various structural components of the bacteriophage T4 ranges in size from several tens of nanometer to several hundreds of nanometer, offering a wide range of scanning dimensions. So for now, we are exploring how to put this target on, how to move it, how do you position it in proximity to the epicenter. For now, we are actually trying to put it on top of that diamond nanostructure, and you can see on the right. So now, to broaden its applications, we are currently building a wide field view setup using this high-speed EMI CCD, which has a 1024 by 1024 pixel array. So each of the pixel works as an individual photon counter with single photon sensitivity. So magnetic field across a 2D area can be picked up by this camera simultaneously, so making it a great fit for imaging applications. As you can see, we can reliably control and monitor the quantum states of ensemble entities in this wide field view setup, but still working on making it a more practical imaging applications and optimizing the overall system. So far, I've talked about our work on quantum sensing towards nano-MRI and micro-MRI. So what we are measuring is tiny fluctuating magnetic field created by nuclear spins. So given this capability, we considered its potential application to study electron transport in two-dimensional systems. And there are many interesting studies using this approach. With NV centers, transport imaging can give you maybe local disorder, viscous electron flow, and Meissner currents, and maybe superconducting vortex motion. So I can give you, in the next slide, a key example of it. So in this paper, they directly imaged the viscous flow of the electron flow in graphene at room temperature using NV centers in Dymo. Actually, Professor Philip Kim contributed to this fine work. So I believe at they used both scanning single spin and wide field view magnetometry, and they show a parabolic flow profile, which is a clear sign of viscous electron flow. And that occurs because at the charging neutrality point, the lack of free charge carriers and strong electron-hole interaction enhance hydrodynamic behavior, allowing the Dirac fluid to exhibit collective viscous flow. It's totally different from the uniform line you can see in normal metals. They also found that the viscosity and scattering rates are the universal values expected at the quantum criticality. So they opened up this exciting opportunity of directly probing viscous electron flow. So this actually raised a compelling question. So can we harness such hydrodynamic behavior to control electron flow in an asymmetric manner? So that's our question with Professor Son, and so he came up with this idea. So there's one intriguing structure and which enables such hydrodynamic behavior with directional flow, which is the Tesla valve. So Tesla valve is a passive device with no moving parts. So fluid flows more easily in one direction than the other. It was invented by Nikola Tesla and Peyton in 1920. So the sketch above is from his original design. So here's how it works. In the middle figure, the flow flows in the blocking direction, and you can see some of it gets around at each segment of the structure, which slows down the overall flow. In the bottom figure, you can see the flow moves in each direction, passing through with much less resistance. In the previous slide I just introduced, they observed the viscous flow of the Dirac fluid in graphene. So building on that, we aim to investigate whether hydrodynamic behavior actually cause directional electrical resistance in graphene Tesla valve structure. In other words, electrical resistance can vary with the direction of the applied bias. So that was our question. So we thought this work could be a compelling experiment to demonstrate the directional electron flow in patterned graphene. Also, it highlights the excellent application of NV-based imaging. These two-dimensional materials like graphene are well suited for NV-centered magnetometry because the NV layer can be brought into very close proximity to the active current channel. So if we could reliably transfer high quality, larger graphene on top of the diamond, then that might open a unique opportunity to observe the local current distribution in the graphene Tesla web structure. So that's what we talked about so far. So maybe after this presentation, I might want to have discussions with you, and then through those conversations, I can refine the research direction and approach so that we can move forward more effectively. So that was it. So far we did an NMI. We're still pushing the project, and we are still have an ongoing development of EMI CCD based MRI system, and hope to do some collaboration with Professor Son on this imaging current flow in Tesla belt structure. So thank you very much.
Thank you for Chucky Kim's talk. We will provide questions. Any questions?
Much the nuclear speeds like carbon-13 will be compared with the field from the carbon.
Yes, natively they're supposed to be like 1.1% of C13 in diamond, but we grow the diamond from the CVD, so it's like 99.99 C12 enriched diamond. So at that time NV center we didn't have any C13 around near 2 nanometer, at least 2 nanometer. So we don't have at that point we didn't have any C13.
But otherwise you would see exactly the same signals from the proton. So it's unless you locked to the loud frequency,
correct,
you don't have it.
Correct.
Any question?
Yeah, thanks for nice talk. So I just want to understand, if MRI detection is sensitive to the spin fluctuations, is it correct?
Yes.
So then how are you going to image the current flow?
Oh. So currently we are thinking DC. So the DC field, we are imaging DC field, and at that point, actually we are thinking about random measurements, which is sensitive to DC field. So basically we flip the spin into the superposition state, and then the phase of the spin actually sensitive to the B field. Yes.
So it's a Tesla lab, somebody did these experiments, right? So I just kind of checked that, and Svenstrup actually claimed that they measured this
electrically.
Yeah, electrically. I think that was in I remember that there is somebody did that, and seems like
actually I searched it last week, and
yeah.
The one I saw was in Nature 2024. They measured phonon transfer in Tesla, and also
2020, there was a paper, or it was a preprint in the archive. I'm not sure. I cannot find the publication versions.
Did they image the?
Not the imaging, but electron measurement. And then, yeah. So,
yeah.
There are some claims out there.
Okay. Yeah.
Yeah.
Always.
Using graphene.
It should be. There shouldn't be diode effect at zero field in linear regime, right? So it's only a finite count.
Yes, it is kind of non-linear vision, so it's
to get to.
Yeah.
So otherwise, outside the relation will.
That's right. Yeah. I think hydrodynamic flow means that it's kind of not, I think, non-linear.
Yeah, you're transferring the momentum somewhere.
That's exactly what we're aiming for. Yes. Non-linear physics, maybe.